Okay, so a Cholesky factorization is S equals the Gramian of R, where R is upper triangular with non-negative diagonal. So how do we produce such a factorization? Well, it turns out that this is intimately connected with the notion of an LD L transpose factorization. So let's see how to do it. So as a step-by-step process, the first thing we do is we apply the PS equals LU procedure. But remember, if you ever need to do a row swap, you immediately know that your matrix is indefinite, which means it's not positive semi-definite, so there is no Cholesky factorization. Also, if you ever produce a negative pivot in U, you also know that you're not going to be positive semi-definite, because a positive semi-definite matrix cannot have a negative on the diagonal of U. So if either one of those two things happens, you can immediately terminate your algorithm and conclude that there is no Cholesky factorization because your matrix is not positive semi-definite. However, if you get past step 1 without needing a row swap and without any negative pivots in U, then you can factor S as L, D, L transpose, where L came from the L and LU, and then D is the diagonal matrix whose diagonal entries are the pivots in U, which is the diagonal of U. And here's the thing, with this factorization, I can split D in 2 by taking a square root, and I can do this using real numbers, because in this situation, the diagonal of U will not have any negative numbers on it. So I can define R as the square root of D times L transpose, and this is guaranteed to give me a Cholesky factorization, S equals R transpose times R. The reason that this R works is because defining R as root D times L transpose allows me to split up S as the Gramian of R, because S is L times D times L transpose. So let's see this in action. Here I have a 3x3 real symmetric matrix S, and I've applied the PS equals LU procedure to row reduce S to U here. Now, along the way, I didn't need a row swap, and also I end up with no negative numbers on the diagonal of U here. So this matrix S is positive semi-definite. In fact, when I get to U, I see that there are no zero pivots, so S is actually positive definite. So how do I produce a Cholesky factorization given this setup? Well, remember, our formula for R and S equals R transpose times R is R equals the square root of D times L transpose. D here is the diagonal matrix whose diagonal entries consist of the pivots in U. So D would have diagonal entries 9, 1, and 1/9. So when I take the square root of D, I get the square root of 9, which is 3, the square root of 1, which is 1, and the square root of 1/9, which is 1/3. Then I have L transpose, where L came from LU, where I inserted the negatives of my multipliers into a lower triangular matrix. And so this gives me my Cholesky factorization. S is positive definite here, so I could factor it as LD L transpose, where D has a positive diagonal. And then I can go further and say S is also the Gramian of an upper triangular R with positive diagonal, where R here is root D times L transpose. So here I see R is indeed upper triangular with positive diagonal. So that's Cholesky factorizations.